online. Rohan Jha is presenting a talk on internet security and cryptography, and he's another MoMaths winner in the writing category this time. And one of his areas of expertise is elliptical curve cryptography. So if he's ready to start presenting, I'll pass straight over to him and we'll hear all about it.
Oh, am I audible, visible? I think I am. Okay. So, hello everyone. My name is Rohan Jha, and I am a senior at Livingston High School in New Jersey. Before I start my presentation, I would like to thank everyone involved with the CMSE for inviting me today. I'm extremely honored and privileged to be here. As Mr. Stevenson said, I was connected to this conference through a competition known as the Strogatz Competition for Math Communication, which is hosted by MoMath, a museum of mathematics in New York City. And I was the winner of this competition in the writing category. So although, as Mr. Stevenson said, my talk is about internet security, it was suggested to me that I should take a few minutes to share the work that won me the competition. So as you can see, I think on your screen right now, we have my submission, which was Math Musings. Math Musings was a magazine I published as a part of a math club that I had started in my school. And really, I started this magazine because I felt like my fellow students had a certain stigma associated with mathematics where people would really shy away from it. However, I never really understood this because personally, I fell in love with the subject when I first, for as long as I can remember now. So I thought that I should make a piece that maybe should spread awareness about the subject and how it is applicable in our daily lives. So here we can see my magazine, and I just like to go through it very quickly, and then I can get to my talk about internet security. So this is just the cover page. Then we have an index. My first article was about I'm of an Indian origin, so I thought I should do something that links math to the Indian culture, and that is why I related it to Indian music. I'm not going to go into detail because I know I don't have much time, but this basically talks about the Hemachandra sequence in Indian music and how it's related to the Fibonacci sequence, and then how that is related to the golden ratio, which many of you may have heard of. Then my magazine talks about magic tricks. So I really tried to link it to even if fields weren't very linked to each other, I tried to link math in every single one of them. In this magic trick, basically uses binary and ternary systems, and it shows how by using math mentally, you can actually do a card trick. And finally, I linked it to traffic jams, which I'm sure all of us have experienced, and this phenomenon known as the phantom traffic jam. Just to quickly note that if any of you are interested or by any of this work, then it is available on the MoMath website, I believe under the heading of Strogatz Winners. As a part of the club, I had invited Professor Eknath Ghate, one of the most renowned mathematicians in India, to give a talk in my school. And this is just some images of us teaching math to underprivileged kids. Yeah, so that's just a little glimpse into the magazine that got me invited to here. But as Mr. Stevenson said, this talk would mainly be about internet security. So I've prepared a 5-minute video about cryptography and internet security because I feel like as our world is becoming increasingly digital, it is very important to understand how secure our information is on the internet and how different types of cryptography are used to keep our information secure. So I'll be talking about the basics of cryptography, and then I'll go into the mathematics behind it in a method called elliptic curve cryptography. So if we could please play the video now.
Over 4 billion people online today. Our lives are becoming increasingly dependent on the internet. Things like online shopping, looking up information, or using one of the various social media sites such as WhatsApp, Instagram, Facebook, Twitter, YouTube, social media sites such as WhatsApp, Instagram, Facebook, Twitter, YouTube, Hike, etc. have become a part of our everyday lives. However, we are also increasingly vulnerable to hacking incidents involving emails, social media accounts, and at times putting even our bank accounts at risk. Most of our online communication involves a message. The scrambling of the message, known as encryption, then sending it to a recipient who unscrambles the message, which is decryption. Cryptography is the science of secure communication. It involves both encryption and decryption of online transactions, creating Over 4 billion people online today. Our lives are becoming increasingly dependent on the internet. Things like online shopping, looking up information, or using one of the various social media sites such as WhatsApp, Instagram, Facebook, Twitter, YouTube, Hike, etc. have become a part of our everyday lives. However, we are also increasingly vulnerable to hacking incidents involving emails, social media accounts, and at times putting even our bank accounts at risk. Most of our online communication involves a message. The scrambling of the message, known as encryption, then sending it to a recipient who unscrambles the message, which is decryption. Cryptography is the science of secure communication. It involves both encryption and decryption. It has many uses, such as ensuring safe and effective online transactions, creating safe passwords, encrypting chats on social media, and disk encryption. There are two main types of cryptography: symmetric key and public key.
Firstly, we have symmetric key cryptography. In symmetric key cryptography, both encryption and decryption are done with the same key. Both parties must have access to this key. Say we have two people, Betty and Steve. Betty sends a message to Steve, encrypting it with the key, which in this case is a red lock.
Steve receives this message and decrypts it with the blue key.
He then sends a different message to Betty, encrypted with the same red lock, and Betty decrypts it with the same blue key.
Some examples of symmetric key cryptography are messaging on social media or sending emails. Then we have public key cryptography. In this case, decryption requires a private key, whereas the key to encrypt is different and can be announced to everyone. Hence the name public key cryptography. For example, 5 people send messages to Steve, all encrypted with the same red lock. Steve then decrypts all the messages with the same blue key. It is important to remember that knowing the public key does not give you any idea about what the private key is. So only the party holding the private key can decrypt. Some examples being net banking and online transactions. Despite our growing dependence on the internet, there is a potential problem with modern-day cryptography.
But first, we have to understand what a one-way function is. A one-way function is a mathematical expression that is easy to calculate in one way, but difficult to calculate in reverse.
In modern-day cryptography, for example, multiplying two large prime numbers to get a product is easy. However, given the product to arrive at the original two prime numbers is very hard. In this case, the product will be the public key, and the two factors will be the private key. Nevertheless, a slim possibility exists to find the two factors. Elliptic curve cryptography, aka ECC, is a public key cryptography technique and provides an even more secure method to find the public and private key. In ECC, we start with an elliptic curve defined by y square is equal to x cubed plus ax plus b,
where a and b are elements of a finite field.
Given 2 points, a and b, we draw a line and find the point where the line intersects the curve, and we reflect that point about the x-axis to find a third point. A line connecting the third point with the point we started with will give us another point where it meets the curve. That point is again reflected about the x-axis, and this way we keep finding new points. We continue this process n times, where n is a very large number, till we reach a final point omega. The initial and final points are public key, and the number of iterations is the private key. Given the public key, it is virtually impossible to find the number of iterations n, which is our private key. How secure is ECC? Arjen Lenstra, a Dutch mathematician, devised a way to compare the safety of different crypto systems by computing how much energy it would take to find the private key from the public key. He put this in terms of how much water it would boil. For an RSA crypto system with a private key of 36 digits, it would require the same energy as to boil a teaspoon of water. Whereas for an ECC-based crypto system, it would require the same energy as to boil all the water on planet Earth.
This implies that RSA would require a much larger key length than ECC to achieve the same level of security.
While crypto systems continue to evolve and become more secure, we can also take some precautions at our end. We should change our passwords regularly. We should also choose passwords which are strong, a combination of uppercase, lowercase alphabets, along with numbers. We should avoid keeping records of passwords at one place. Finally, we should not share personal information or data with anyone over the phone or email. In conclusion, cryptography is one of the most important areas today, and although certain forms of it are extremely secure, there are still some advancements in mathematics that could lead to further improvement in the long run.
Right, so that was the short video that I prepared for this conference about cryptography. And I wanted to highlight the mathematics behind it and its importance in our daily lives. And then I tried to end it up with tips, which everyone probably knows by now, but I thought there's no harm in reiterating it, I guess.
That's really good. Really good, Ron. Great video. And certainly really topical at the moment and pretty much any time for security. I'm just waiting to see if anyone's got some questions for Rohan at all. And some comments about being pretty late in New Jersey, so you're up pretty early.
It is 4 a.m. I'm not up early. I just didn't sleep really. I was pretty excited.
Yeah, maybe while we're sort of waiting for some questions to come in, maybe talk about the MOMATH as well. And I'm not sure that everyone would be that conscious of it. I mean, I think a lot of people would know about it, but something you can tell. I've got a question up as well now.
Sure. So I'll just quickly talk about MOMATH. So MOMATH is a museum of mathematics, which is in New York City, and it's pretty well known in the country, and I'm pretty sure abroad as well. And basically, they've linked up with a professor at Cornell University, which you may have heard of, called Professor Steven Strogatz. And they hosted a competition called the Strogatz Competition for Math Communication, which was basically the participants had to submit works that were basically spreading awareness in the field of mathematics and how it's communicated. And yeah, so my Math Musings was a part of that competition. And if anyone's interested, they can check it out on the MOMATH website. It's MO and then math.
I think a lot of people will be doing that. There's a question now. So if you could just read the question out and see how you go with it. Thank you.
Okay. Very nice presentation. To explain these kind of questions in a simple graphical way isn't trivial. And I think you've done very well. Thank you so much. I really appreciate that. Congratulations. Sorry, my face cam is kind of blocking the question. Congratulations. In ECC, what is the impact of the eccentricity of the elliptic curve? Right. So basically, what I was trying to convey when talking about elliptic curve cryptography was that it's probably the most secure crypto system in our modern day life. And so basically, by what I meant when I was talking about its eccentricity was that in comparison to the other crypto systems, it is extremely hard to break, as I explained with the example of the boiling of water, which I found was a very interesting experiment, where in RSA crypto system, which is more the traditional one that's used till date, it would require the same energy to break it as to boil a teaspoon of water, whereas an elliptic curve crypto system would require all the water on planet Earth to be boiled to equate it to the amount of energy needed to break it. Right. So there are many types of ECC. Which specifically are you talking about when you give the energy example of boiling water? Right. So I'm basically talking about, I tried to maybe average it out, I suppose, but I'm talking about mainly the shape of the graphic that I'd shown, where it was y is equal to, I gave the equation of the elliptic curve, and then the private key was based on the number of iterations that the curve went through to achieve the points, which was the public key.
All right, that's fantastic. Thank you for the talk, and it was wonderful. And congratulations on winning the Steven Strogatz Prize as well. Thank you for your talk tonight.
I'd just like to thank everyone once again for inviting me over here, and it's been an honor to speak to all of you. And I feel very privileged to be surrounded by so many great minds.
And hopefully we'll be back on terra firma in Poland in 2021. So it'd be great to hear the long version as opposed to the shorter version.
Of course, yeah.
Thank you. And so if we could ask Pavel.
1 second. Sorry, there's something.
Thank you. If Pavel Periakita and Michael Wren can be ready. So we local from Poznan, from the local university, the Adam Mikovic at Poznan, and a lot of the stuff around Enigma and codebreakers. I saw something about a koala competition as well that had been published, I think, by Pavel, which is very close to my heart in Australia. But I'm really interested to hear what they've got to say as well. And if they're on, I'll hand straight over to them.
Hello, I think I'll start if I could get the presentation. Perhaps I will find it. Oh no, it's not mine. That's mine. Okay, so good morning, ladies and gentlemen. I will give you a short presentation about the people who broke Enigma, whom we are very proud of because they are people from our university. I think that you all know what Enigma was. It was a machine, a cryptography machine used by the German military during World War II. This is what it looked like inside. It was an invention of Scherbius, who started selling it in 1923. It was pretty quickly adopted by the German military in 1926. And the other things about this timeline you might have heard, but possibly you might have heard some incorrect things. For instance, maybe you thought that Turing broke Enigma, or maybe you thought that heroic American soldiers captured Enigma from a sunk U-boat. I don't know, but in reality, it was a little bit different. Since the Germans adopted a cryptography machine which was then unbreakable by standard techniques, we knew that we had to do something. The Polish, of course, listened to all the message traffic, but we couldn't decrypt it. And in 1929, there was a cryptography course launched at our university. It was then called Poznan University. And it was attended by, among other people, by Jerzy Różycki, Henryk Zygalski, and Marian Rejewski, the people who became famous later for breaking Enigma. And in a pretty short time, because they started working on the problem in 1930, in 1932, Marian Rejewski recreated Enigma just knowing how it worked. He never saw the actual Enigma. He just knew mathematically how the algorithm worked. And he decrypted the first messages. From then on, we started decrypting all the German messages pretty much. In 1935, he invented the cyclometer. That was the first electromechanical device that assisted in decryption to make it easier than using pen and paper. And unfortunately, in 1938, the Germans, before the war, the Germans made some changes to Enigma. They added more rotors. They changed a little bit how it was used for encryption. It made it much more difficult to break. But in 1938, in November, so pretty quickly, Marian Rejewski constructed the bomb, which was a device that broke the Enigma, the changed Enigma. And also, Henryk Zygalski designed his sheet method. Zygalski's sheets were large sheets of papers with perforations. And when you stacked them and looked how the light shone through, you could speed up decryption a lot also. But you probably heard about the bomb. Maybe you heard about the Turing bomb. Turing had nothing to do with it. It was Rejewski who invented the bomb and then later instructed Turing in its use. Because in 1939, Polish passed on all the techniques, the decryption techniques, to the Allies, which is normally never done. If an intelligence agency manages to break another country's ciphers, they never admit that. They never admit that. They don't even show their allies the decrypted messages, because that could expose the fact that they can decrypt the cipher. So they just will tell them, based on our operational techniques, we know that they planned this and so. The Polish not only admitted to everything, they passed all the techniques to the Allies. And because of that, in 1939, the British started expanding the Bletchley Park Center, which later would, during the war, would serve as a center for decrypting Enigma. And they started recruiting mathematicians for the center. And this is, in general, this break of Enigma is a very important point in history of cryptography, because before that, ciphers were broken by people who had humanities backgrounds, people who were very good at solving crossword puzzles, who knew lots of languages and so on. But those people were not able to break Enigma, and it was a sort of a paradigm shift that mathematicians started to break ciphers. It continues to this day. Well, right now, maybe computer scientists do that, and who knows how it will be in the future. Maybe physicists will take our place. Okay, but let me show you the people who are responsible for that. Those are the people who organized the course. Maksymilian Ciężki was the boss of the German ciphers, part of the Cipher Bureau, and he got Zdzisław Krygowski, who was a professor of our university, to teach math on this cryptography course, and Antoni Paluch was a military man who taught our cryptologists the military ways of cryptoanalysis. And those three people who later broke Enigma were Marian Rejewski, Jerzy Różycki, and Henryk Zygalski, who were mathematicians. Why am I emphasizing this point so much? Well, the heart of Enigma were the rotors. Maybe you saw that on some pictures. It looked like this. The rotor on one side had sort of small metallic plates, and on the other, spring-loaded bolts. And when the rotor touched, current could flow through those connections. Of course, inside the rotor, those connections were not straight through inside the rotor, because the point was to mix things up. And so the Enigma worked in the following way. When you pressed a button, it sort of worked like a typewriter. When you pressed a button, there weren't impressions on paper, only light bulbs would go on. Perhaps G would light up, because the current took some path inside those rotors and flew into G. However, when you press the button, at least one rotor would click, and then the configuration inside the rotors would be different. So then the next time you pressed A, well, maybe some other letter would light up. Here it's C. So it sort of changed with every letter you typed in. That's why the people who approached this as a crossword puzzle, something like that, were not able to break it. Somehow those changing configurations of rotors had to be accounted for, and that was the job for mathematicians. And Rejewski made use of theory of permutations to do that. He made some observations. I will give you two here. If for a given rotor setting, pressing the letter A would produce B, then it was symmetrical. If you pressed B, it would give you A. Well, because we know, of course, Rejewski didn't know that because he did not know what Enigma looked like, but we know that the current doesn't care which way it flows, so it had to be symmetrical. Also, Rejewski noticed that pressing A would never give you A. You couldn't ever get the same letter when you pressed a given letter, which we now also know why. Well, the current couldn't sort of loop back on itself. It had to have a path to flow through. But those observations are rather trivial, and everybody, including the people who approached this as a crossword puzzle, everybody could make that. However, Rejewski used lots of math, which I will thankfully spare you because we don't have time. And he made some much more interesting observations, used a mathematical theory of permutations. One of his theorems were later called the theorem that won the Second World War. So it was pretty significant. He noticed that pressing a letter from one cycle, because he decomposed the connections between the rotors into cycles. You know that all the permutations can be decomposed into cycles. So pressing a letter from one cycle would always produce a letter from another cycle from this permutation of the same length. And also, if pressing A would give you B with some rotor setting, then if you pressed a letter that would be to the left or to the right on its cycle, then it would produce a letter that would be to the left or to the right in B's cycle. And this seems like magic. I mean, there is no way to arrive at those conclusions, to make those observations, without actually writing the enigma, writing enigma out as a series of permutations. And this is why mathematicians were necessary. If you want to learn more about, because I just glanced at them, if you want to learn more about Rejewski's methods, he wrote his memoirs. He wrote his memoirs in his 70s, and they were the basis of a book that was published at our university. It's a book that is both in Polish and in English. It's Polish on one side and English on the other. So if you buy it, I'm sure you'll be able to understand it. And he discusses all the methods that they used in the Cipher Bureau. If you want to learn more about the history of Enigma, you could learn a lot from Marek Grajek's book. It's called Enigma Closer to the Truth, Enigma Bliżej Prawdy. Unfortunately, I don't believe it's available in English, but, well, Polish is a beautiful language, and I'm sure that you can learn it easily. This is the bibliographical information of the books I mentioned. Thanks very much for people who contributed to Wikipedia by sending pictures, because I used them a lot. And in case you wanted to learn more about cryptography, the sort of a crossword puzzle cryptography that is before all the math, you could also learn the Simon Singh's The Code Book. It's a very good book to do that. And if you want to ask me questions, this is my email. I will wait with answering questions until after Paweł's presentation, because he will tell you a little bit about what is there to see in Poznań. Thank you very much.
We would like to invite you to visit an exhibition dedicated to those who first broke Enigma codes in 1930. Those who first broke Enigma codes in 1930s. It's available online now. The exhibition is located in the so-called Cipher container. It's a small building which looks like an Enigma machine. Inside the container, there is a timeline of important events in the history of cryptology. By the way, students of the Poznań course in 1929 learned the basics of the described ciphers. Now everyone can try to act like an adept of cryptology. It also holds a number of interactive displays that offer children and adults a way of learning some simple manual cipher methods. Everyone can play the role of cryptographer and try to break the code. An educational center honoring that the conquerors of the Enigma codes is to be opened in 2021. I think it's a step closer now. It would be a state-of-the-art museum. One of the main aims of the center would be to popularize maths and computer science. I mean, that maths that is behind. We encourage you also to try your hand in a city, a tourist game, Code Breakers. You can get to know Poznań from the time when the cipher course in 1929 took place here, as well as follow in the footsteps of the secret agents to break a secret message. It's available online. The Enigma container and the city game I told about before were developed by people behind the international cryptology game Code Breakers. Its game starts in August. It would be available in English and Spanish, German, and French, and Russian, and of course in Polish language. In a minute you'll see a short video trailer about the game. At the end, I would like to recall Neil Koblitz, his words. It was in his article in 1997 where he stated the impressive value of cryptography as a teaching tool. Thank you very much for your attention.
I think we're back, so I can certainly see you, Michael, and Pavel as well. So we've got a few questions, so we might start throwing to those really quickly. And if you want to read them out and then answer away.
So how much credit, if any, should Turing get for breaking Enigma? I think it's a question to me. And I might be just a little bit biased, but my answer would be none whatsoever. Turing did a lot of work in computer science in general. He did some work in cryptography as well, for instance, in breaking Colossus or in creating voice cryptography during World War II, which was pretty impressive. But as for breaking Enigma, no, he didn't do anything really. In fact, he had to be instructed personally by our code breakers because he couldn't understand the documentation they sent him how to break Enigma. That happened in France. Anyway, he was, of course, smart enough to adapt those methods later on because as the war progressed, Polish were occupied, so they couldn't work in Poland on breaking Enigma. All the work was done in Bletchley Park, pretty much. And well, that's pretty much it. I don't think he should get credit for breaking Enigma specifically.
Cool. I'll go to our next one.
It's a comment. World War II in Europe began. Oh, okay.
Oh, sorry. I think that's slow on my
began
side.
with Germany invading Poland on September 1st, 1939, and Russia invading Poland on September 17th, 1939. Understandably, we need to make Enigma gain overtones. Well, I agree, obviously, because well, the people who broke Enigma were from my university, so I will plug it in any way I can. But I actually think that some of you might get more mileage from cryptography before Enigma, cryptography that was done using simpler ciphers, because if you teach, for instance, high school, well, fluency in permutations and explanations like, oh, the permutations form a group and so on and so forth might be a little bit too difficult. So I'm lucky enough that I teach university students, and I pretty much start at the third year. I don't even teach first and second year university students. So my students can understand when I talk about cryptography, but if you want to get people interested in math, then maybe simpler ciphers would be better. None. I teach cryptography at a university. I sometimes do some sort of invited lectures for high schools and even middle schools, but I never go lower than that.
I guess they sort of wonder what I might be reading that differently about whether it's suitable for primary school as well as high school.
Sorry, what do you mean?
Whether cryptography could be taught at primary school as well.
Oh yes, absolutely. Just not, but I personally don't teach cryptography at the primary school. But yes, I've had lectures for middle schools as well. And I'm sure that with some adaptations, they would be suitable for primary schoolers. Well, it's just, playing who can outsmart whom. Children love that, so it's a good way to get them interested.
Could you hear me now?
We can hear you.
Yes, I can hear you, Pavel.
The question.
I think it's.
Sorry.
I think it's worth to say that Dermot Turing, Turing's nephew, wrote a book where he shows that Enigma code breaking process as a relay race. So it is a good source of knowledge, I think.
Okay, so the question is just wondering if the Polish contributed as much to the Russians after World War II. I'm not sure. There might have been cooperation in code breaking, but I don't know anything about that. It's probably still classified.
Yep.
For example, Rajewski came back to Poland after the war, but it was impossible for him to work as an academic. So it was reality in Poland like this. Thank you.
I'll put the next one up. Sorry, thanks, Pavel. I think this is more a comment, but if there's anything we can add to that.
It's my personal opinion, as Michael just said, that more simple ciphers might be better for younger students, but I personally also teach public key cryptography, including the math, but with 2-digit numbers, to high school students. Well, yes, certainly. And actually, public key cryptography might be better because there are number theory problems there, and they are easy to explain. They use concepts that everybody understands at that level. Again, here, for instance, in Enigma, a group theory and permutations would be very important. And in RSA, well, you can get by with multiplication and addition pretty much. Well, modulo, you need to know the modulo operator.
Many of us love computer science unplugged, as Fran said. We have there 3 activities about cryptography. It is for teenagers. I mean, they can understand a lot.
Yes, I traditionally give lectures during Poznań Mathematics and Science fairs about digital signatures, and I do that for high schoolers, really. But I also use RSA for that.
Excellent. So I think we might keep moving. Thank you both very much. It's been wonderful to hear that story. I think everyone's enjoyed it and probably wishing we were actually in Poland and rather than being online, but that'll happen in 2021. So I'm sure Poznan is not going anywhere. And everything will still be there when we get to arrive and we have the full-blown conference. So just the taster has been fantastic. And we'll pass on to our next presenter, who almost needs no introduction, has been to all of them, has been an intricate driver for it, and with Michael Fellows, a formidable educational partnership to sort of in the background driving CS Unplugged, Bebras in Norway as well. And her specialty is parameterized complexity and algorithmic design. That's a bit of a mouthful, but I'll hand over to you, Fran, and love to hear from you again.
Thank you very much. My slides will be uplifted. I'm using slide presentation. And I chose modeling with graphs. And graphs is a little bit of a funny word because when we think about graphs, we usually think about X, Y coordinate systems. But in computer science, graphs are more than networks. They're dots that are connected by lines. The dots are sometimes called nodes or vertices connected by lines. And the dots can represent any item of interest, friends, and then lines can represent friendships. The lines represent relationships between the dots. Could be airplanes, and the lines connecting the airplanes could be distances apart, or websites and popularity, or radio frequencies and signal strength. As Brett said, my research area is algorithm design in the parameterized complexity framework. And I wanted to find something to present to teachers and to the rest of us that related to this. And so I chose a topic of great importance. It's how to model conflicts with graphs, with these networks. And the reason that I think it's useful for teachers is because these can be models of just about anything in real life. So you can use this idea in any subject that you are teaching. So for example, we could talk about air traffic control. Air traffic controllers need some kind of support systems in case a group of airplanes is in trouble because there may be some conflict. By conflict means there might be interference. So each node in this graph on the right, the black dots and lines, the dots represent the aircraft, and the edge represents the possibility that those two aircraft that the edge is connecting are in conflict. That means there's going to be an interference, maybe a crash. So we want to find a set of aircraft that we could remove or issue commands to ask them to change their course so that all those edges are eliminated and there's no risk of interference. Another example of this would be social distancing. Here we have an event. These are people at the event, and an edge between them means that they are standing too close together. We want to find a few people to ask to move so that there will be no conflicts. No one will be standing too close together. So if we ask Sophie to leave, then the edge between Sophie and Marco and Sophie and Anne will be deleted along with the dot representing Sophie, and there will be less conflict. There's still a conflict between Anne and Walter and Betty and Walter, but if Walter leaves, then the remaining people will have no conflict. Everyone remaining now is at a proper distance. Here's another example. This example has to do with sequence alignment, multiple sequence alignment. Multiple sequence alignment is a way of arranging DNA sequences or RNA or protein sequences to identify regions of similarity from which an evolutionary tree can be read off. Similar sequences will share a common ancestor. So the sequences are compared pairwise when they're aligned, and they're given a score. The larger the score, the more dissimilar are the two sequences. So we'll choose some threshold value, maybe 0.5, and everything over with a score larger than 0.5 would be in conflict. They would be too dissimilar. So we'll draw a conflict edge between the genes that are too dissimilar. That's what the edges indicate. And what we now want to find is a sequences to remove so that all the remaining sequences are similar. So we could remove sequence 1 and sequence 3 to remove the conflicts. Sequence 1 and sequence 3 are said to be covering the conflict edges. They're called a vertex cover. That's the technical terminology. And once they're removed, then the remaining sequences are all similar. The conflicts has been resolved. Conflict graphs can be huge. These protein sequences graphs can be 10,000 vertices. The technical term is vertex cover, and we have a K vertex cover problem. Given a graph G and a parameter K, a number, can we remove all the conflicts, that means removing all the edges, by deleting K vertices? When we delete a vertex, we're also deleting whatever edges are touching or connected to that vertex. So there's by the degree of a vertex, we mean the number of edges that the vertex has as an endpoint. And there are 3 reduction rules that are used by algorithm designers and programmers when they're working with this vertex cover problem. There's a degree 0 rule. That degree 0 means there are no edges, 0 edges that are touching vertex V. So we'll delete those isolated vertices. They're not covering any edges. They're not touching any edges, so they're not involved in any conflict. There's the degree 1 rule. Vertex R in this picture has degree 1. And we want to get rid of the edge RS. Well, we could get rid of edge RS by taking R into the vertex cover, and that would take the edge with it. Or we could take S into the vertex cover, and that would take the edge with it. And it's more advantageous to take S, because if we take vertex S, we'll not only delete the edge RS, we'll also delete any other edges that S is touching. Another rule is the high degree rule. Suppose in this picture, notice that there's vertex U and it's connected to 4 other vertices. So the degree of U is 4. Suppose a question said, can we delete all these edges by removing 3 vertices? Well, the answer would be no, if we had to delete all 4 of those. But the answer could be yes, if all we had to delete was vertex U, because it would be also deleting the edges connected to it. So the question asks, can we delete all conflicts by deleting K or fewer vertices? And if the degree of U is greater than K, we must take U into the cover. Otherwise, we would have to take all of the other K vertices, and that would just be too many for our budget. Now I'm going to run through a little example, which takes several slides. But as I do it, imagine that there are 2 children playing a kind of a vertex cover game. Now, it's not a game in the sense that we have rules and regulations and a winner. They're only taking turns applying those 3 reduction rules that we just looked at. But I'm putting it out there because it's suggestive of a game, and maybe somebody in the audience who's a puzzle designer or likes games can think about how you might use vertex cover to create a game. Anyway, here's 2 little kids looking at this graph, and they see that A and B are vertex 0, degree 0, so we'll delete those, just scoop them away. And if we want to get rid of all the vertices all the edges by just deleting 4 vertices, we have to take vertex F, because otherwise we'd have to take G, J, K, N, and M. So let's just do that. And we'll put F into our vertex cover. Then we notice that we have degree 1 vertices. There's G and there's M. So let's take H and N into our vertex cover. Now we're down to, we've taken F, H, and N, and we've taken rid of all the degree 0 vertices. Now we've basically reached our budget. We have only one more to take. So let's just take Q or R because those have degree 3 and there we would, or F, I suppose, Q or R. Well, it looks like I have R twice, sorry. So I took Q, and we have now reduced this graph to a triangle and a rectangle. It's a much smaller graph than we started out with. This reduced graph is called the kernel, or the hard part that didn't get deleted, didn't get simplified with these 3 reduction rules. Well, to summarize, there are lots of ways of modeling problems with graphs. Here's a different way. Real-world problems may have networks of networks, community groups based on common location, interest, occupation, or protein interaction networks with similar functionality. And these networks have boundary issues, internal issues, community issues. So we need to find ways to model networks of connected networks. Another issue is diverse solutions. Usually when we see a mathematics problem in a textbook, many aspects of the problem are ignored. That's deliberate. People strip away as much extraneous information as they can to get down to a manageable and understandable mathematics problem that we can apply our mathematics tools to solve. But all of this extra information is known by the person who wants to use our solution and our methods. For example, in that social distancing problem, the person who's asking people to move aside may notice that some guests are on crutches. So they would modify their solution, the solution that I presented. Or the air traffic controller, they know a lot that's not taken into account in the graph. They may know that it's better to ask smaller aircraft to change their course in preference to larger aircraft. Or it's better to ask aircraft which are cruising to change their course in deference to those who are taking off or landing. So really, it's a new idea, possibly, that instead of finding one optimal solution, for instance, it may be more useful to find a significantly diverse collection of good solutions from which the controller can choose based on his or her extra knowledge. This diverse solutions idea has just been accepted for a paper at one of the top artificial intelligence conferences. So we're very proud of that. So what about with the kids? What can kids do? Well, one thing, students can find new reduction rules for vertex cover and other important real world problems. There are many reduction rules already developed, but more are needed. And as I mentioned, you could imagine playing a game using implementing a suite of reduction rules. It's not a game, but it's a suggestion of a game. And importantly, students can create small instances of vertex cover graphs that are difficult to solve. Teams can challenge each other, create a tricky graph that the other team cannot resolve. Why is that important? Because training data is the most important part of machine learning, part of artificial intelligence that Andreas mentioned. When Alexa or Siri makes a mistake in interpreting your request, that data is used to make the system smarter. We need these training sets. So that's the end of my talk. Basically, I would like to let the teachers know that these kinds of problems, these graph modeling with dots and lines, are perfect for any age group. Thank you very much.
Thanks, Fran. That's really, really good. We actually have a unit on graphs and networks at that runs in Tassie for some of the courses in year 11 and 12, and it would be the most popular unit that students do. So it's really good. I'll just throw that question up to you. I've got one question anyway, so.
I don't see how to, I don't see it. Okay. One of the challenges may be to choose a proper threshold. What are some of the techniques for that? Well, that's a very good question. It really depends on the situation and on the particular problem and on the particular issue. If you're talking about multi-sequence alignment, there are many issues that are involved in choosing the proper threshold for those. But for other issues like, I don't know, a distance between airplanes in an air conflict scenario, the controller would know more about that because that's a particular issue with which they are familiar. Oh, sure, I'd be happy to. I'll make sure it gets put on. Mm-hmm. Yes, it's the IJCAI conference. Yes. Oh, that looks good. CNRS. Oh, thank you. Thank you. Yes.
That was pretty quick. I'm just waiting to see if there's any more questions, but I mean, that's been fantastic, Fran, and certainly great to have you coming at the bookend at the end of the conference of the time. And a year can't go fast enough. And I was certainly talking about graphs to students today who were quite excited and really enjoy that sort of mathematics. And it really does, it sort of rocks their boat in terms of excitement, and they don't find it a chore at all. They find it quite straightforward and quite easy to do.
It's pretty a lot of intuitiveness to it as well.
It is. It's actually quite fun. I think there's another question I'm trying to. I'll see if I can get that up at the moment. Yep.
In the social distancing problem, are the number of points for people fixed? If there's a violation, does it suggest alternative positions? Well, I just made up this problem because we're experiencing social distancing here in Australia and other places in the world. Usually that would be, what is it now, Brett? Is it a meter or a meter and a half to be apart?
Yeah,
I know
1.5. It changes all the time, doesn't it?
It's changing all the time. At our stores, we have little X's made out of tape put on the floor so that everybody knows you have to stay that far apart from each other, or else there's a shopping basket measure that you have to stay within, apart 2 shopping baskets length. So, and as far as the number of points for people, we're talking about if we have a room full of people, each person can be represented by a node in the graph.
Yeah, I think it's a really good application at the time, and I think we've gone from 4 square meters to 2 square meters, and Tassie's lucky. We're really like Tim as well. We have no active cases and have been about 40 or 50 days, so we're just trying to stop Victorians coming over. But hopefully that all gets fixed pretty soon. There's been with the rapid response to it. I might sort of keep us.
We want everybody to come over to Poland next year. That's
I think anyone who's been along. I think anyone who's been along to our taster tonight, or today, or this morning, or this afternoon, or wherever it is that you're listening, I would doubt that anyone who's been and listened to the wonderful presentations, they would not want to be there if they could possibly be there. That said,
everybody, let's just let everybody know the new date.
It's been a pretty decent sort of run. I mean, it has been pretty hectic.
Fantastic. You guys in Poznan, you are tremendous. Thanks for making all this so happen. It's really beautiful. So what are the dates? So it's July again of 2021, and it's starts on the 2nd next year. we'll have a community day where people are invited, any of the attendees are invited to bring their favorite activities, and we'll present them hopefully outside. And everybody from the Poznan community and all the presenters and their family are invited to come. I'm not quite sure which date that is yet, but we'll make sure everybody gets to hear about it, and it's on the web.
Yep, got it down. Starting as the 2nd of July. That's right, Fran, isn't it, on the Friday?
Yep.
So, and that usually travels for about 4 days. So it gives people a chance to digest the information. It was a very rapid sort of abridged version tonight.
Yeah,
but just awesome. And I think the decision to do it online was a very good one, and to build up for 2021.
It's wonderful to see. I wish more people could be seen, because it's fun to get to know each other and hear what each other's interested in, and it'd be great in the future to have more of a general discussion. Yeah.
Yep.
That's
good.
Yes, you are all invited to Poznan.
Yeah.
Thank you, Paolo. Thank you so much.
There's a couple of questions.
I just asked to have an opportunity to say thank you. I'm very honored to be in this small conference. I enjoyed very much, and I thank you for the opportunity. I hope you enjoyed as well. And hopefully we can meet face to face next year. Hopefully.
Yes.
Thanks, Judith.
Yeah. Bye.
Bye, Judith. Bye, Judith.
Bye.
Bye.
There are some questions we might try. I'm trying to get them to come up on Publish, but I'm not sure whether that's working or not yet.
I see one, Brad. It says, are paper presentations solicited in addition to activities? And the answer is yes, they are. And what we're looking for is innovative and new ways of communicating mathematics and computer science to all. And so that's the main part of this agenda.
Yeah, they do go through a process. Yep.
Oh, Professor Gopal, you could submit an abstract. Thank you.
We would love to see it.
The other thing I noticed when I was in India, I was in several places in Chennai and then further north and there are many people there that are designing activities that are, that was mentioned by somebody else here. Oh, by Tim Bell, designing activities that do not cost a lot of money or require a lot of fancy equipment or things that people would have to go out of their way to acquire. Simple things. So I think those are very important in this world today, to make sure that we have methods of showing our work, showing mathematics using simple things.
Yep, here. And we do have one more question I'll just throw up on the thing now.
Oh, Krishnan, this is the first time we've done it online like this due to necessity, but this is will be the 5th CMSC. The first was in Darwin in 2013, and then JAM organized it at the Institute for Mathematical Sciences in Chennai. That was the second one. And then Rüdiger Reuschek in Germany, and then we had it in Wellington, New Zealand at the Art Institute with Jonathan and Alice Milne. And so this one in Poland will be the 5th.
Yep, there's just an okay, thanks. And yep, it certainly has got bigger, Fran. We had certainly a good audience tonight, and it'd be nice to have the numbers big again for Poland. So, I mean, why wouldn't they go to see Poznan, to see the Enigma machine, and listen
that's
to our wonderful
amazing.
presenters? Mm.
As far as I know, our webinar was recorded, so it probably would be available to watch it later.
Oh, that's wonderful. Thank you for doing that. That's just great. Because Malgorzata said that there were almost or over 200 people registered.
Yep.
It's really terrific. And
I guess we have to thank Mal. Sorry?
And you,
I was going to say we have to thank. You go first. Yeah. I mean, I was just going to say we should thank Malgorzata, who's been doing all that work in the background tonight and has been sort of hidden, and Matus as well. So lots of things have been happening in the background that,
yes.
I mean, I've been being put back on. For the first hour and a half, I was probably dropping out every 10 minutes and Matus was putting me back on. So obviously worked at the end. So tech support was wonderful. And I think that was a real win.
It's a real win. It's a real win. And there are a joining conference that you're going to before this one. Isn't that right?
The CME conference as well. So that's, and I can't remember where it is, but somebody might remind me, especially someone in Poland who may go into that as well. Gdansk. And so they've sort of teamed up together and they've put theirs over for a year as well. So that's exciting.
Yeah,
and every time there's a CMSC, there is a research day workshop. So there would be one on parameterized complexity as well at probably the day following the CMSC workshop. And also I think there's a Lego workshop that's scheduled as a special event as well. Plus the theater, plus the music, plus the community day. I think everybody's going to have a great time.
I'm so glad.
Sounds good. You live there all the time, Pavel.
Okay.
Well, I'm going to have to go. Thank you, everyone.
Yeah, me too. Bye-bye, everybody.
Bye, everyone.
Bye-bye.
Thank you, and take care.
Thank you. Take care.
Thank you. Take care.
And we can't push the red button.